This is Nanoscape. I'm Seth Zimmerman.
And I'm Erin Spain.
On this show, we venture into the frontier of nanotechnology
with experts in the field who are turning the science of small into the next industrial revolution.
This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University.
Today, we are talking with Dayne Swearer, a Northwestern University scientist who is passionate about using nanoscience to develop new sources of energy to drive chemical reactions, offsetting the global demand for fossil fuels.
Dayne is an assistant professor of chemistry and chemical and biological engineering at Northwestern and a member of IIN's vibrant nanoscience community. We welcome him today to discuss the long-standing importance of nanoscience and energy, unique ways nanomaterials harness energy, and new research emerging from his lab, which is studying questions at the interface between nanophotonics and chemistry. Welcome to the show, Dayne.
Thank you, Erin. Thank you, Seth. Appreciate you having me.
So you came to Northwestern in 2022 with the opportunity to build your own lab from the ground up. So tell us about your career so far and your research goals and what it was like starting a lab from nothing.
Yeah, it's a really great question and something that you're not always prepared for, is kind of walking into an empty space, recruiting your first graduate students and postdocs to work on big, important, and new problems and really build from the ground up. So a lot of my motivation is in the area of energy and sustainability, and that's obviously a really large space that you could explore scientifically. One of the main challenges was identifying those problems that we're going to work on and exactly how we're going to do that. And so starting September 21, even before I got here, I recruited my first 3 graduate students. And by that following summer of summer 22, we were in the lab building up some of the first experiments that we had. So that involved just incorporating different things like mass spectrometers, FTIRs, gas lines, mass flow controllers, laser control, so on and so forth, to do some of the photocatalysis work that we've been working on here.
I mean, I think I saw pictures of cranes and things, bringing things into your lab space. Is that right? I mean, this was really, as you said, building from the ground up.
Yeah, my lab occupies a corner of the Catalysis Center. So I'm not sure exactly, Erin, what pictures you saw, but part of that rebuild was integrating new air handling systems into the building's suite on the 4th floor on the roof. And so I was definitely here early on Saturday mornings at 6 a.m. watching the cranes lift air handling units up onto the roof of the building that I now work in to deal with some of the stuff that we do in my space.
Northwestern has very strong interdisciplinary research environment because nano isn't just one field. It's not one area of science. It's not just chemistry or engineering or astronomy. It's all over the place. So how have you adapted to that kind of approach here at Northwestern? And how important is that interdisciplinary element to this area of study?
Yeah, nanoscience is the ultimate interdisciplinary field of scientific research. So I'm a chemist by training, and I have a co-appointment right now in the Department of Chemical and Biological Engineering. And so, a lot of my work is taking things at the atomic scale and the nanoscale and thinking about chemistry and chemical transformations at the very, very fundamental level, but then also thinking about how we can scale that up and make an impact on society. You can't possibly span multiple orders of magnitude when you're thinking about these types of problems, even going out to the planetary scale, without having help from people with different and diverse backgrounds of their own training. So somebody that kind of spans 2 departments at Northwestern, I see this very firsthand all of the time, even with collaborators in material science and electrical engineering. There's always things that every person brings to the table to address some of these large-scale challenges. And it's been extremely rewarding working with colleagues that have backgrounds that are completely different from mine. I learn so much on a day-to-day basis just talking with people from kind of across the aisle or in this way in Tech Hall, on the other side and different wing from the one that I reside in.
So you mentioned some of the goals of your lab, and that has to do with climate change and how can we reduce our reliance on fossil fuels? Talk to me a little more broadly about this. The global threat of climate change, carbon emissions, and our reliance on fossil fuels are major challenges of our time. Describe this threat to me in your own words, and what could happen if we don't reduce greenhouse gas emissions dramatically in the next 2 decades?
Climate change is a major issue, major threat, and I think scientists and engineers and pretty much everybody collectively across the planet needs to do their own contribution to make the world a better place for tomorrow. I think maybe I'm more inclined to speak specifically on what I'm doing to address that problem and what my research is. And that really revolves around the idea that all of the materials and molecules that we use as a society are often things that come from the background, right? We don't really see where the base materials for the clothes that we wear or the fertilizers for the food that we eat, sometimes even the transportation fuels to go visit our family for Christmas or to get to work every morning. A lot of that stuff just kind of shows up at our doorsteps. And the chemical and energy industry is one of the largest industries on the planet, and it's also one of the hardest to decarbonize. And so decarbonization here basically just means, it'll likely be very difficult to take all the carbon out of future processes. But what my group is really doing is trying to use different techniques to reduce the overall energy demands of making the materials and molecules that we're going to need for tomorrow. And so we've got a lot of different strategies that we're exploring to do that. But that's really the basis of what we do to address climate change, make a little bit of a dent there towards that larger picture that we don't always see.
So the world needs to move, obviously, quickly to increase our renewable energy production. But science, as we all know, doesn't always move particularly fast. So how do you and your team stay focused? What keeps you motivated when these problems like climate change are just incredibly overwhelming when you really start thinking about it?
Within my lab, the way I would say that we're focusing on this is that we focus on reactions that make the building blocks of the chemical industry. I mentioned all of the materials that we use, right, for food or fertilizers or transportation, things like that. All of those are end-use primary things that consumers see. So consumers being all of us as individuals. But upstream of that, in the chemical industry, there's advanced intermediates, which are more specialized chemicals. And then even further up is what I say are the building blocks. And so those building blocks are things like hydrogen and ammonia and ethylene and propylene and aromatics. This relatively small class of about 18 to 20 different molecules, that's what we focus on and what we target. My kind of driving hypothesis of a lot of my research is that if we could develop ways that take those 18 base chemicals that everything else in the industry and the world is really based on, and we can use sustainable energy, derived from solar or wind or even nuclear to power chemical processes using electrified means or even renewable heating, that could be a really effective way that as an industry and as a society, we can reduce our overall energy intensity for some of these key processes that are just so fundamental for the chemical and energy industries.
When you're in your lab and working and you've made a breakthrough, do you guys celebrate or do you just think, oh my God, we have so much further to go? Or do you actually enjoy that for a little bit and then move on? Or what's the day like when that happens?
As you mentioned before, sometimes science can be slow and it takes a long time to get discoveries. I think every scientist in the world probably wants to walk in the lab every day and discover something new that's going to change everything. But just, frankly, the fact of the matter is that it takes years of dedication, honing your craft and learning a particular reaction even to be able to make progress towards these particular things. And so in terms of celebrating, I try to, I'm the kind of person that, puts my head down and is always kind of focused on the next thing. But particularly when my students have a win, whether that be the project that they were working on for the last couple of weeks finally has a good result, to celebrate that. Even tonight, actually, right after this, I'm heading home to go bake dinner for everybody. We're having a party at my house just to celebrate the year and the things that have worked out really well for us. Celebrating a lot of those wins. And I would say sometimes those wins and those milestones might not be a new discovery, but, somebody getting a fellowship or somebody getting a recognition, those kind of things need to be celebrated because they're just as important for career growth and folks, especially graduate students coming out and going towards their PhD.
So on this podcast, we sometimes like to ask people about some of their favorite examples from the past and how nanotechnology has been used to really impact the world around us.
When I think about nanoscience and how it impacts industry, I think of an often cited chemical process called the Haber-Bosch process. Haber-Bosch is what we use around the world right now to make a chemical called ammonia, NH3. So relatively simple molecule that's produced by taking nitrogen from the air and hydrogen gas that's produced through a process called steam methane reforming, and combining those together at high pressures and high temperatures with a particular type of catalyst. And so this was a development that came about in the early 1900s and then was industrialized through high pressure reactors in Germany by the BASF company. So Fritz Haber and Karl Bosch were the guys that this process was named after, but Alwin Mitasch was the chemist and engineer who developed all of the catalyst that is still in use today. And so through these systematic developments of nanodomains of iron oxide and potassium oxide and aluminum oxide that all mix together to make this Mitasch catalyst, that is what is the basis for all ammonia that's produced on Earth today. And you might think ammonia is just one of these chemicals, one of these building blocks, but it's often cited as like the detonator of the population explosion in the 19th century. So if you think back in 1908, when this process and this catalyst was first found, world population was about 1 billion. And I think we're pushing over 8 billion today. And the reason for that is because all of the synthetic fertilizers that we have come from these industrial processes that use these nanoscale, nanodomain catalysts to make that work. And so everybody listening to this podcast right now in some way has been impacted by Haber-Bosch chemistry, nanoscale catalysts, and so on. And so again, a lot of my work is how can we develop new catalysts and catalysts that maybe use alternative forms of energy to make the materials and molecules we need.
Your lab is taking a page out of nature's playbook, and you're using light as a primary source of energy to drive chemical reactions of industrial and societal importance. So tell me about that, and why do you think this approach is gaining traction?
In my lab, we develop a particular flavor of nanoparticle. We call them plasmonic nanoparticles. And so plasmons are these collective electronic oscillations that exist in small metallic materials. And so what that means is that light carries an electric field. Light also carries a magnetic field. That's what makes it an electromagnetic wave. And we use those physical properties to push on the very small light electrons that exist within the metal. This is the same reason why copper wires are used throughout your home or throughout buildings, because those electrons are free to move throughout the wire. But when we take the copper, or you could also use silver, you could use gold or other types of metals as well, and you shrink that down to sizes that are much smaller than the wavelength of light, those electrons that are confined within that nanoparticle respond extremely well to the optical cross-section of the light that's being shined onto them. And so this is, again, it's an interesting one because it's a nanotechnology that's been used since ancient Roman times for making colored glasses, things like stained glass windows, things like that. But now what we're doing is we're taking that same type of confined nanoscale metal, we're integrating different catalytic active sites into that, and then we're using the energy that's contained within light to drive chemical reactions on the surface. I think that's particularly interesting and important because light can be renewable or sustainable. You can get light energy from the sun, although the density of light that we get from the sun is maybe not the highest, but you can also use things like artificial light, so LEDs or even lasers, to have a lot of energy within a photon packet, hit those catalysts at a given point in time. And one thing that's come out of my research since I've gotten to Northwestern is not just using these plasmonic metal nanoparticles for these catalytic reactions, but rather the unique way that those plasmon resonances and those moving electrons actually interact with molecules. And so right now, our group is doing a lot of work on trying to understand exactly how electrons transfer energy to those chemicals or molecules that are sitting on the surface, and trying to draw connections with other areas of research and sustainability and energy that has maybe similar chemical physics associated with that. And so we're looking at things like low temperature plasmas, which also have similar types of reactivity that right now that connection isn't super clear. But hopefully over the next couple of years, my group's going to be able to disentangle what happens when you have high energy electrons within a metal nanoparticle catalyst and high energy electrons maybe in the gas phase when they interact with a nanoscale catalyst, and how we can have selectivity towards these reactions that we're interested in.
You mentioned stained glass, and I never really thought about how stained glass is made. So do you guys, I just now have this mental image of your lab just decorated with these intricate stained glass windows, and I assume that's obviously how it is. Or is that like a test for people coming in, like make me a stained glass window and see if you can hack it?
I never thought about making that a requirement to join the lab, but if we start having stained glass window production be part of it, that could be really interesting. It's a great visual, and I actually really, really like that set. The difference is that stained glass, those nanoparticles are confined in a matrix. So you've got the silicon dioxide in the glass that really wraps around them, and that's why they keep their colors for hundreds and hundreds of years in cathedrals around Europe. But what we really do, especially with a catalytic reaction, is you want the molecules that you're interested to get to those nanoparticles on the surface at the same time that the light is, so that excitation can transfer its energy into the molecules that we're really kind of targeting for these chemical transformations. So it's a little bit different, but we do have some really interesting colored powders that we've got in the lab. And of course, you're welcome to stop by anytime if you kind of want to see what we got going on.
Definitely.
And again, this work is all part of that greater goal to open up new pathways for chemical transformations using renewable resources.
The industry already works really, really well, right? All of society is really built upon traditional processes that use heat, mostly coming from the combustion of natural gas and other petroleum products, to make these things work. So we have a great playbook set out in front of us of how these transformations typically happen. And we can learn a lot from that, but we collectively, as the entire field, have to move towards a type of processing where we can use electricity, whether that be electrochemical reactors, where we use those electrons directly, or kind of what I do is wireless electrochemistry with light or with plasma to make some of these things happen. If we're able to do that, that's going to make a huge difference in the ability for society to create what they need using electricity from renewable sources. And I think that's an extremely important goal that we should really be targeting.
Little over a year ago, you received the prestigious 2023 Packard Fellowship in Science and Engineering from the David and Lucille Packard Foundation. This fellowship is awarded to the nation's most innovative early career scientists and engineers. Tell me about this award and how the opportunity really has impacted you since then and the lab here at Northwestern.
The Packard Award was really transformative in terms of the way and the direction that I'm taking the group's research, and really lets us springboard off and try some risky things and some new things that maybe I wasn't thinking about when Northwestern decided to hire me in 2022. The primary area that we're now able to explore are these low temperature or non-thermal plasmas. I mentioned previously in the conversation that the chemistry between a non-thermal plasma and a plasmonic nanoparticle, I believe, are very similar to each other, despite the fact that these right now appear to be two fairly distinct fields of research where you've got groups that focus on one or focus on the other, but I believe there's some real interesting connections there. And so with the Packard, what we're able to do is kind of jump into this new space, run some experiments and some tests to see if my hypothesis that the chemistry of plasmonic particles and non-thermal plasmas interacting with other types of catalysts are similar, or maybe they're different. And how are they different? And I think that's really exciting. It's also kind of been born out of this idea of climate change and the importance to address that. It was basically me looking at what happens when CO2 is both causing climate issues. So really the reason why we have climate change in the first place is because of the greenhouse effect. And so CO2 is in our atmosphere and it blocks heat from getting out of the atmosphere and being transferred into the cold darkness of outer space. And so we're blocking an atmospheric window. And the reason that happens, even though that happens on a planetary scale, is because of individual quantum vibrations of those molecules. And so I was kind of digging in and thinking a lot when I was writing the Packard Fellowship of what that is and what causes that. And my question was, what happens when CO2 vibrates? Could we take advantage of that? And that's how I kind of wound down this path of how we could use plasmons and how we could use plasmas through vibrational excitations of CO2. So for those of you that maybe you're thinking, what's a vibration of CO2? Just that molecule bends and wiggles. And so those molecules are always moving and active in that way. And so we're taking advantage of that and asking questions that are related to light and electricity and how we can use these forms of energy to drive chemical reactions that are kind of similar to this.
How rewarding is it to be able to really dive into, like you said, a topic that wasn't on your radar, and the ability and the funds really to be able to go down a different path? What does that feel like for you?
It's very exciting. I think one of the things that's been really exciting about going into this new line of research, even though it was unexpected, is that I'm learning a ton every day of new things, new techniques, new approaches, a whole new area of science, and being able to connect the dots between what I'm really an expert in plasmonics, and what this whole other field is, and seeing how similar they are, but also different at the same time, is something that I'm really thankful for having the opportunity to be able to do. And hopefully with these maybe divergent fields, being able to bring those together, make a big splash on the overall goal of my group to be able to change the course of industry and industrial processes for energy and sustainability.
So now looking ahead, how do you see nanotechnology reshaping the chemical and energy industries in the years to come? If you could predict, you had the crystal ball, what would you like to see happen?
Hopefully within the next decade or so, we see a major shift in the way that the energy and chemical industries are kind of using alternative energy sources to make the materials and products that we need, rather than, the same old of burning natural gas or petroleum and continuing to emit carbon dioxide as part of these processes. So things like photochemistry or plasma chemistry or electrochemistry, all of these depend on nanostructured surfaces, engineered surfaces that have particular reactivities associated with them. And this has been going on for a number of years, but I think we're at a cusp of history that the technology is finally matured enough to the point that we're going to start seeing it much more widespread. And maybe one thing that is unique about what nanoscience can do in the development of these catalysts is to think about the modularity of certain types of reactor systems and bringing smaller scale opportunities rather than the large chemical manufacturing plants that folks often associate with these things that take up, square miles of space. Start having chemical reaction systems that are based on renewable energy that can be kind of plopped down in the tractor trailer when and where it's needed for certain aspects. And I think that's really exciting and something that maybe the type of work that me and many others around the nation and the world are doing could end up enabling.
Any closing thoughts, maybe like how can people keep track of your work? Do you have social accounts you want to throw out there that people can keep track of what's going on with you?
You could visit our lab's website, sites.northwestern.edu/SwearLab. Best way to keep in track via social media right now is just started up a Blue Sky handle, Dayne.Swearer on Blue Sky. And I think I'll be maybe starting up there a little bit more in terms of keeping in touch with the community. So reach out to me.
Well, thank you. Thank you for all of your insights today, sharing what's going on in your lab and some of your crystal ball predictions for the future. We appreciate it.
Hope they come true.
Thanks so much for listening. This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Be sure to follow this show on Apple Podcasts or wherever you listen to podcasts, and be sure to give us a 5-star review.
For more information about IIN, go to our website, iinano.org/podcast.